Hello, everyone. This week, Cristina Dalfó will tell us about the spectral of lift of digraphs and the factorized lift of graphs.
Okay,
Cristina?
thanks. Thanks a lot for letting me to explain the work that I did recently. I'm going to talk about the spectrum of lift of digraphs and factor lift of graphs. And this is joint work with Miquel Àngel Fiol from the Universitat Politècnica de Catalunya and Sonia Pavlikova and Joseph Sirany from the Slovak University of Technology. Okay, then my talk has two parts. Don't worry that they are not long. The first part is about lifts or voltage graphs and how we can find the spectrum of a voltage graph when we have cyclic groups or abelian groups. In fact, we also solved the problem for any group, but there was too much things to say. So, but then we generalized the voltage or lift graphs or digraphs, and we call them factor lift. And then in this case, I'm going to give the results on cyclic groups and on any group. And first of all, I want to explain why the factor lift were necessary. Okay, then let's begin with the lifts. Well, some of you know a lot, I mean a lot about lifts and voltage graphs. But let's begin with an introduction. Sorry that well, can you see my cursor? Yes? Okay.
Yes.
Then I'm going to pass. Oh no, this doesn't work. Okay. Okay. Then, first of all, a bit of notation. Gamma will be a graph or digraph. When it's a graph or digraph, we can write it in this way, with a vertex set B and arc set E. Then, given a finite group G with generating set S, a voltage assignment is a mapping from the set of edges to the elements of the generating set of the group. Then we say that the pair gamma alpha, or sometimes only gamma, is a voltage digraph or graph. And we say that a voltage digraph, or no, this is the lift digraph. This is the small, the voltage digraph is the small, and the lift digraph, or sometimes only say it lift, gamma to alpha, is the digraph with vertex set, the product of the elements of the vertex set of gamma by the elements of the group, and the arc set is also the product by the elements of the arc set by the elements of the group. And there is an arc from a vertex in the lift digraph, from a vertex UG to a vertex BH. If and only if UB is an edge in gamma, and H is G times alpha UB, of UB, where alpha is the voltage assignment of this arc. Well, then first we are considering that we are on the cyclic group, zeta M. And some years ago, with Mirka Miller, Joe Ryan, and Joseph Sirany, who joined us very soon, we defined this polynomial matrix. Mirka Miller was very fond of this matrix. She said 10 years ago, she said that it will give us a lot of results. It was true, but I didn't know at that time. And well, this matrix is a square matrix indexed by the vertices of gamma, and the entries are polynomials. And these polynomials have coefficients, this alpha 0, alpha 1, etc., which are 1 or 0, depending of if UB is an edge, and is an edge with voltage assignment I. And then here we have this Z to the voltage assignment. This is like zeta to 0, zeta to 1, Z to m minus 1. And then let's see a small example. If between the vertex U and B, we have all these arcs from 0, 1 up to m minus 1, then the entry UB is this polynomial 1 plus Z up to Z to m minus 1. And let's see an example, which is the Allegre digraph. The Allegre digraph is this digraph on the right. And on the left, we have its base digraph. I represented the arcs with voltage 0 with a thick line. And for example, the polynomial matrix of the base digraph is given here. For example, between C and D, we have two arcs. Between C, the entry CD is zeta to 1 plus zeta to 4, because the voltages are 1 and 4. Then we have zeta to every one of the voltages for all the arcs between these two vertices. I think is it clear? Yeah? Okay, then we can construct the Allegre digraph from the base digraph on the group Z5. And then we have to repeat this digraph 5 times. And for example, there is a loop in vertex E with voltage 1. Then this means that I have to add 1, I have to join the vertices E, but adding a copy. In the big digraph, we have 5 copies of the base digraph, and then actually there is an arc from E0 to E1 to E2, etc. Then I have to add 1 copy. And the same for the other arcs. If there is a 0, then I am in the same copy. And in fact, this polynomial matrix, this polynomial matrix, when Z is equal to 1, is the quotient matrix of a regular partition of the lift gamma to alpha. Here, continuing with the same example, on the right, I have again the Allegre digraph in a very different way, the drawing in a very different way, but it's isomorphic to the previous one. And if we, for each color of the vertices, we replace all the vertices in the same color by 1 vertex, we will have a quotient digraph, and the quotient matrix will be this one, which is the same that the polynomial matrix when zeta is 1. Well, let's see what happens for the cyclic groups. In fact, in my example, I was in the cyclic group. Then we continue with the cyclic group. Well, it was known, in fact, it was a result by Gottsiel, a long time known result, that in our notation says that if gamma is the base digraph and alpha is the voltage assignment, and we have the cyclic group, G, then the matrix is, and B is the polynomial matrix, then the spectrum of the polynomial matrix when Z is 1 is included in the spectrum of the leaf diagram. In other words, that the spectrum of the small digraph is included in the spectrum of the big digraph. Some years later, with Michelangelo Fiol, Mirka Miller, Joe Ryan, and Joseph Sirany, we could prove that with the same notation, the spectrum of the leaf digraph is the spectrum of the polynomial matrix when Z takes the values of all k roots of unity. Because here we are in the cyclic group ZK. So from the spectrum with the polynomial matrix, we can find the spectrum of the big digraph with the spectrum of the small, not part of it, if not the complete spectrum. For example, continuing with the Allegre digraph, the polynomial matrix that I showed you before, it was here. If we compute the spectrum, we found this spectrum here. And of course, this spectrum, it can be complex. In this case, it has complex values, complex eigenvalues, and it depends on Z. But then we only have to give to the Z the 5 roots of unity, because we were in Z5, and then we obtain all the spectrum of the Allegre digraph. Yes, then we could, with the polynomial matrix, I repeat because I think this is an important thing, that from the spectrum of the small digraph, we obtain the complete spectrum of the big graph. This polynomial matrix is only when we are in the complex, in the cyclic group. Well, let's see what happens when we have abelian groups, and I mean abelian non-cyclic. If we have a cyclic, then we do as I just said. Okay, for abelian groups, as an abelian group can be expressed as the product of different cyclic groups, then we also construct a polynomial matrix. But now we don't have one variable, we have n variables. So the entries of this polynomial matrix now will have this coefficient that it's also, as before, 1 or 0, depending if there is an arc or not between these two vertices, and with n variables that are to the voltages. And let's see an example. Sorry, here we have the Hoffman-Singleton graph, which is the graph on the left. And if I want to work with this graph, I will need a matrix 50 times 50. It's only a word to write the matrix. Well, it was known, in fact, it was proved by Jana Shagova, that the Hoffman-Singleton graph can be constructed as a leaf of a base digraph on 2 vertices. We go from 50 vertices to 2 vertices with voltages in the group Z5 by Z5. And is it as before, but now all the voltages have two entries because we are in a product of two cyclic groups. For example, in B, in vertex B, there is a loop with voltages 0, 2, and 0, minus 2. Well, then we have to construct this, to write this polynomial matrix. And for example, in the entry B, we will have, as the voltages were 0, 2, and 0, minus 2, we will have Z to 0, double B to 2, plus Z to 0, W 2 minus 2, which is this factor here. Well, then we found the spectrum of this matrix, but now I have to give to Z and W the 5 roots of unity. And giving these values to Z and W, we obtain all these eigenvalues that, as I said, are these values here, 7 ones, 2, 28 times, and minus 3, 21 times, which is known because the spectrum of the Hofmann-Singleton graph was known. Then for abelian groups, we only have to add more variables, but we can use the polynomial matrix. Okay, let's see what happens with factor leaves. And let's begin with a really small introduction. The first question is, why factor leaves? What happened with the leaves? It was not enough. Of course, the leaves or voltage graphs or digraphs work perfectly well. But the question is that we found some examples that couldn't be solved with leaves. And then we have to define these factor leaves. And here I have two examples. On the left, there is the two-token graph on the cycle on 9 vertices. And on the right, the two-token graph on the cycle on 8 vertices. It doesn't matter now the definition of the token graph. Most of you, a lot of you know, but here it's only two examples. Then on the left, we see that we have a perfect cyclic symmetry. Then we can use the leaves on the cyclic group, and it's perfect. We obtain the spectrum, everything works. But when the order of the cycle is even, we have some problems. And if we define an orbit like the set of vertices that are in equivalent positions, for example, in this example, 1, 2, 2, 3, 3, 4, 5, 4, 5, etc., this orbit has 8 vertices. The orbit formed by the vertices 1, 3, 2, 4, 3, 5 also have 8 vertices. The following orbit also 8, but in the center we have an orbit with only 4 vertices, and this is why our symmetry breaks, and we cannot use the lifts because it doesn't work. Okay. Now gamma is going to be a graph, and every edge is considered to be two opposite directed arcs. Now we define the set of vertex with B and the set of arcs with A. Boldface A is the adjacency matrix of gamma. And now we are going to have a group G and a subgroup H. And G bar H is the set of all right cosets of H in G. And their number is given by this expression, which is usual in group theory. And then we said that now we don't have a voltage assignment, but we have a combined voltage assignment. And why combined? Because as before, we have a graph, a group. Alpha is an ordinary voltage assignment on the arcs, of course, as always in the case of graph, with the property that converse arcs have inverse voltages. But now the difference is now that we have weight or voltages, if you want to call them, we normally say weight on the vertices. And every vertex B will have a subgroup of G, a subgroup that we call omega of B, which is a subgroup of G. Then it's a big difference, because now we have weight on the arcs and weight on the vertices. And the graph gamma with the combined voltage assignment is called a combined base graph. And the factor lift with respect to the corresponding combined voltage assignment is the graph, or it could be a digraph or even a mixed graph, such that the vertex set, now the entries, the vertices have two entries. One is the usual number of the numbering of the vertices, and the second is H, which is which belongs to this right coset. And for every arc UB in the combined base graph, there will be an arc in the factor lift from the vertex UH and finishing at the vertex BK, if and only if, of course, both subgroups belong to the right cosets, if and only if the intersection between H times the voltage on the arc A and K is non-empty. Let's see a small example of this. Let's suppose that we have a group Z12, and the H is the subgroup 3 times Z12, that is the set 0, 3, 6, 9. And K is another subgroup. And for example, the alpha, the voltage on the arcs is 0. Then in the factor graph, the vertex UH is adjacent to the vertices BK, BK plus 3, BK plus 6, and BK plus 9. And this is given by the set H. Let's see what happens on cyclic groups. I will show you two examples. The first example is the Johnson graph J42, or the octaedron graph, which is represented on the right. And we will have the group Z4. Then on the left, we have the combined base graph. And of course, every arc has the corresponding voltage, but you can see that now the vertices have weights. In the case of the vertex U, the weight is 0. That is the trivial group. But the weight on the vertex, on the vertex B is the subgroup 0, 2. And of course, we can make a standard lift. And if we make a standard lift, we obtain the graph represented and called here B. The problem is that it doesn't give the graph that we wanted. We wanted the Johnson on the right. Then it's for that we need the factor lift, because with the leaf, we obtain another graph that it doesn't interest us right now. But it's curious that if we could join these two vertices, B0 and B2, in only one vertex, and these two vertices, B1 and B3, in another vertex, then we will obtain the octaedron. And here, as before, I represented with a thick line the edges with voltage 0. As you can see in the octaedron, the vertices have two entries, U or B, and the corresponding subgroup. Well, let's see another example, a bit more involved, a bit more complicated. Now we have the 3-token graph on the cycle on 6 vertices, and we are on the group Z6, and the subgroup 0, 2, 4. Then this is the 3-token graph on the cycle of 6 vertices, and all the vertices in the same, in equivalent positions, I call them U. And here I have U0, U1, U2, and all the vertex U form an orbit. All the vertices B form another orbit, and here I have B0, B1, B2, etc. The same happens for the vertices Y that also form an orbit, 0, Y0, Y2, Y1, Y2, etc. But what happens on the orbit of vertices X? That we only have two vertices X, not 6 as in the other orbits. Well, then we construct the combined base graph, but now the weights on the vertices are 0 for vertices U, B, and Y, but the weight on the vertex X is 0, 2, and 4. And the R's have the corresponding voltages. Okay, we consider that we are on the cyclic group Zn. And then we realize it, of course, working with these weights on the vertices is not so comfortable. But then we realize that we can construct an associated base graph with the same vertices as the combined base graph, and with all the vertices have the weight 0 or the trivial group. But this comes, well, this is great. Now we can remove the weights on the vertices, but there is a price. We have to pay a price for that, and the price is that now for every element on the weight of a vertex, we obtain, if we have R elements, that becomes R new arcs. This is the price. We can remove the weights on the vertices, okay, but we have new arcs that we didn't have before. In fact, it doesn't correspond to the graph that we have, are extra vertices. And with these new R arcs. Well, now the polynomial matrix of the associated base graph, for each arc UB, we will have the voltage I, because here we added I to these arcs. And the UB entry of the polynomial matrix has the term Z to I. As always, Z to the voltage. Well, and here there is our result, if I can maintain here. Okay. And this is our result, as I said. In this result, there's a lot of notation, and then it looks like it's something complicated. No, but I wanted to show you that we have a result. It's not only examples, that we could prove this result. And in fact, I also wanted to write the result because here I only speak about eigenvalues. But in fact, the result gives also the eigenvectors. And in this case, the eigenvectors, the entries of the eigenvectors have to satisfy, have to satisfy this condition, which is a numerical condition. It doesn't matter now which is the condition, but the question is that we can find not only the eigenvalues, but also the eigenvectors. Then let's continue with the example of the 3 token on the cycle on 6 vertices. And here I have to come back to the drawing. If I see this graph, this vertex, that it's all the vertices have two levels, because sometimes it's more useful one than the other. Well, in this vertex 0 to 4, or also called x 0 to 4, we have adjacencies to 3 vertices B in lilac color. Well, then analyzing all the adjacencies, analyzing all the adjacencies, we can see that vertex 0 to 4 is adjacent to 1 to 4, which is the vertex B, which is 0, 1, 3, plus 1 copy, and is also adjacent to 0, 3, 4, which is vertex B plus 3, and adjacent, my mouse is very sensible to any movement. Okay, and also adjacent to the vertex B minus 1 copy. Then the entry xb in the polynomial matrix, we will have zeta to 1, zeta to 3, and zeta to minus 1, because these are the number of the copy, plus 1, plus 3, minus 1. And we do the same for all the other vertices. Here, when I have an arc underlined, it means that we have two arcs between these 2 vertices, and then it was a way to differentiate one from the other. But it's only that. Well, and then if I write the polynomial matrix, and here I have to confess that I ordered the vertices in a non-usual way. Here the vertices are called U, B, Y, and X. But you can change the name. It doesn't matter the name of the vertices. Well, then in position X, B, we have the entry that we just see in the previous slide. And the same for all the other entries. And then when we have the polynomial matrix, we only need to compute the eigenvalues. In fact, this matrix is the same as, well, it's in another way. This matrix corresponds to the matrix obtained when we have a combined base graph, that is, with weights on the vertices. These 2 matrices are different, but if we multiply the last row of the matrix by 1 plus zeta to 2 plus zeta to minus 2, then both matrices are equal. And why we have to multiply by this factor, the last row? Because the last row corresponds to vertex X, and the weights were 0, 2, and -2. Well, in a way or in another way, we obtain the same polynomial matrix. Well, and when we have the polynomial matrix, we give Z the values, in this case, of the 6 values of unity, and we obtain all these eigenvalues. But there is a small problem. Here, in line 2 and line 3, we obtain these two lines. We obtain these two lines twice because they correspond to zeta to 1 and to zeta to 5. And then, in fact, we have 6 lines by 4. We have 24 eigenvalues. If now we come back to the drawing, here, this graph has only 20 vertices. Well, then there are 4 vertices that are spurious. And for the adjacency matrix, these vertices are always 0. Then, if we want to know the spectrum of our graph, we only have to remove these spurious 4 zeros. And then we obtain this spectrum that it was the problem that we wanted to solve. Okay, let's see what happens now when we have non-cyclic groups. The idea is more or less the same, or the idea is the same, but now the computations are a bit more complicated. Because now we will have to work with the irreducible representations of the group with dimension T. And then we call GU the subgroup associated to vertex U, which is the sum of the irreducible representation of all the elements corresponding to this vertex, to the subgroup of this vertex. And now we construct not a polynomial matrix, but a block matrix, and the entries are also matrices. And the entry UB is the irreducible representation of GU times this sum, which is the irreducible representation of the voltages of the arcs, of all the arcs between U and B. Each of these entries is a D plus D matrix, and the block matrix is a dk times dk matrix. And this is the result. Don't worry, I'm going to give an example. The example is easy. The result looks not so easy. But well, here we need a lot of notation. The important thing is that we obtain this multiset of eigenvalues with the spectrum of the block matrix on the irreducible representation rho R, multiplied by the corresponding dimension and the union of all these for all the values of R. And what the result says is that we obtain a multiset B that contains this number, the sum of n u, non-zero eigenvalues. And the spectrum of the factor lift is the multiset B minus Z, where Z is a multiset that contains this number of 0. Okay, and let's see the the promised example. Here, our example is the graph on the right. It's an example, it has no name because it's an example that we thought. And on the right, we have the combined base graph. Of course, as before, we can do a standard lift. But if we do a standard lift, then we don't obtain the graph that we are interested in. We obtain another graph. Well, okay. But our graph, we want to obtain the spectrum of the graph on the right. Well, here, for example, on the combined base graph, on vertex B, we have a semi-edge. This is because we need to add 1 to the degree, and a loop count as degree 2. Then we need a semi-edge, but it works the same. Okay, here the edges without voltage means that the voltage is 0, or in fact is the identity. And here, the weight on the vertex U is the whole group that in this case is the diedral group D3. The weight on voltage B is E, the identity, and the weight on voltage W is E, A, and A squared. Okay, and now we only have to go to a web page on group theory or a book. There is also books on much before the web pages. Okay, then we went to a web page or a book on group theory, and we see that the diedral group D3 has these two elements A and B that have to satisfy these expressions, and that this group has order 6. One moment. Okay, and now the matrix B is the 3 times 3 matrix given by is this matrix. And here I repeated the combined base graph because otherwise we don't know what happens. For example, the vertex B have 3 arcs. One with voltage B, one with voltage A, and the arc with voltage -1. These two as have 0, then is 0. Well, the same as I did for the entry BB, we have to do for all the other vertices. And then in this web page or this book on group theory, we found this table that say which is the irreducible representations R0, R1, and R2 from all the elements of the group, which are E, A squared, B, AB, and A squared B. This is known. Well, now I have, for example, to compute row 0 of G1. Again, I've repeated the combined base graph. In G1, I see that the weight on the vertex U is G, that is D3, the diedral group D3, that is the complete group. And then I have to add all the values corresponding to row 0. Then I have 1 plus 1 plus 1 plus 1 plus 1 plus 1 is 6. If I want row 1 of GU, then I have to add all these numbers, 1, 1, 1, minus 1, minus 1, minus 1, which is 0. And if I want to compute row 0 of GB, GB has only the element E. Okay, sorry. Then row 0, I have to take only the element E, which is 1. Then is 1 for row 0 and for row 1. And row 0 of GW, as W has the elements E, A, and A squared, I have to add only the elements corresponding to A, E, A, and A squared. Okay, the addition of these 3 is 3, and the addition of these 3 is also 3. And then let's see how we obtain the I have a bit of time. Okay. How we obtain, for example, in the block matrix, the entry BB. As I said in this formula before, just in case you don't recall exactly, row of G1 by the sum of row of alpha of A. Okay, in this case, I have row of GB, row 1 of GB, because I wanted the entry of row 1. I have this one, row 1 of GB, sorry, row 1 of GB is 1. This is 1. And I have as B, and here the vertex B have these 3 arcs. I have to add row 1 of A, row 1 of A to minus 1, and row 1 of B. And then I have 1 plus 1 is 2, and A minus 1 is the same modulo 3 as A squared. Sorry. Row of A. No, sorry, I didn't have the E. I have A squared, or A minus 1, and B. 1 plus 1 plus minus 1 is 1. Then 1 times 1 is 1. Well, and we construct these matrices, B of row 0 and B of row 1, with this formula. But what happens with the matrix of row 2? Well, as you see in the table, now we don't have numbers, now we have matrices, but the computations are now with matrices, but are equivalent. And we obtain this big matrix. Well, and now here the zeta is the 3 elements of unity. Well, now we have to compute the eigenvalues of B of row 0, of B of row 1, and of B of row 2 when zeta is the 3 roots of unity. And we obtain all these eigenvalues. Okay, but here I have 3 plus 3, 6 plus 6, 12 eigenvalues. But my graph was this on the right, which has 6 plus 3, 9 eigenvalues. Then this means that I have to remove 3 eigenvalues, 0. It has to be zeros with the adjacency matrix. Then I mark them with an asterisk, and then we only have to make the union of all of these values except the spurious ones, and we obtain the spectrum of our graph. Okay, I finished with that. These are some of my references because I couldn't write all of them. And thanks a lot for listening me. And if you have any question.
Thank you, Cristina, for the nice and very clear talk. Any questions from Cristina?
Thanks to the people who clapped.
Go ahead.
Okay. Hi, Cristina. Hope you are well.
Hi, Safed.
Thank you for this talk. I really enjoy your talk. So I have one or two random questions. I don't know if it will be connected with your stuff, with spectral. I'm interested in combinatorial properties of these factored lifts. Do you maybe have a construction of a regular graph? All constructions that you gave as examples are non-regular. Do you maybe have a regular graph construction?
I don't know if you are asking for regular graphs or for non-regular.
For a regular graph, for a regular construction for a regular graph.
Well, I have some. No, this is not. Sorry, this is not regular.
I checked all the
all of them were non-regular.
Non-regular.
I don't think. I think that it can be applied also for non-regular. For regular, sorry. But I should check just in case what happened with regular graphs.
How to construct them? Okay.
Yes. I write it so I don't forget.
Okay. One more question about slide 8. On slide 8.
Sorry?
Can you go to the slide 8? Can you go back to slide 8, to page 8?
8, yes.
Yes. So you have one example there.
Yes. This is the Allegre digraph.
This one. Okay. So if you you group these colors in some cells, and I noticed that these cells are now giving you equitable partition of this graph.
Exactly.
Do you have any results regarding that? Do you always get some equitable partition with these cells, or this is just?
Well, I only wanted to say there's a particular case. Sorry. I only wanted to say that a quotient matrix is a particular case of the polynomial matrix. In fact, I don't care now about quotient, but there is the case that when z is equal to 1, we obtain a quotient matrix. Which quotient matrix? Well, I don't know. Some of a regular partition or equitable partition. Well, this is to say that our definition, it's like more general than the quotient matrices. Because in a particular case, we obtain a quotient matrix. Sorry, but I think that the octaedron is a regular graph. Not? This was, yes, it's a regular graph. Then nothing special happens with a regular graph. And in fact, I think that Hoffman-Singleton is also regular. Hoffman-Singleton, where I have the Hoffman-Singleton. Yes, well, here it's difficult to see in this drawing with the 50 vertices, but it's also a regular graph. Then everything works.
Okay, thank you. Thank you.
And even the Allegre digraph is regular. But it's regular as a digraph, of course, because it's a digraph. It's regular as a digraph.
Yeah, next slide you get equitable partition. It's also regular.
Yes,
Need to be regular.
yes.
Okay, yes, okay, yeah. Okay, thank you.
Okay.
I probably missed what you mentioned about it. So when you find all the eigenvalues with the lifted graph, when the example was Z5 times Z5.
Sorry, I couldn't follow you so quickly.
So you have the sigma graph. The last example is the first.
Signed graph?
Like the last one, you use the group Z5 times Z5.
Yes. And what is the question?
In that case, to find all the eigenvalues of the lifted graph, you just assign that to be the fifth root of unity. What if the group is not like Z7 times Z? No.
Why
Z8.
do know the group?
No. I mean, like if the group you have is Z5 times Z5, you use the fifth root of unity.
Yes.
I
have. In the case of abelian groups.
Yeah.
Yes.
What if the group is like Z8 times Z4?
If I could do it with another group?
Not for this graph, for other graphs, like the corresponding.
Yes. This is only an example. You can do it for whatever graph that can be that its base graph, it's a product of cyclic groups.
Yeah. So for the case of Z8 times Z4, you just use all the 8th root of unity?
When the two are different.
Yeah.
Well, then suppose that I have zeta 4 and zeta 8. Then here we replace the value for the 4 roots of unity, and the case of W, the 8 roots of unity.
Yeah.